Oh, that makes sense. Yeah. 0.09012.
Yeah.
Okay, we got 12 minutes to get this started, and we'll need every minute of it. 4.6, the last section. We have an application that we commonly use for exponential and logarithmic equations. We've mentioned before, called exponential growth. And exponential growth can actually be thought of as two kinds of problems. We can have growth problems and we can have decay problems. They are the same thing essentially. They have the same formula. But here we go. Our formula for something that is growing exponentially or decaying exponentially, either the population or the quantity is growing over time exponentially or it's declining exponentially over time, is something along these lines. And this is a formula I'll give you for the test. You don't have to memorize this. You just have to know how to use it. Alright, so these variables stand for these things. That y right there is, you can think of that as our present quantity or the quantity or the population at time t. For some specific point in time, this is the population, this is the quantity, this is the amount. Okay, let's call that the amount or whatever t is. That value in time. That value of time. Okay? Y sub 0 is going to be our initial quantity, our initial amount. How much stuff are we starting with? This is at time 0. Okay? Now, why does that work out? If you don't understand what I'm about to do, I'm kind of okay as long as you remember that this number is our starting amount. If I'm starting at time 0, when I take anything and I raise it to the 0th power, I get 1, right? So at time 0, this is 1 times whatever that number is, which is that number. So this is how much I'm starting with. Okay? K is our growth rate. Now K could be positive or negative. And whether it's positive or negative is going to determine whether we have a growth problem or a decay problem. Okay? So if K is positive, if it's greater than 0, then this is what we would usually call growth. But if K is negative, if it's less than 0, then this is a decay problem. And then T, of course, stands for time, right? So over time, our population is growing or it's decaying, something to that effect. Okay? Generally speaking, this is our simplified sort of growth or decay kind of problem. Okay? Now, two quick definitions. There is something that we commonly call the double time. And these are for growth problems. And the double time is appropriately named. This is the amount of time necessary for a quantity to double. Okay? So the other definition is the analogous idea, but for decay problems. Okay? And this, some of you have probably heard of before. It's called the half-life. Y'all heard of half-life? When do people talk about half-life? Yeah, in regular everyday conversation. Yeah, good call. No.
Decomposition.
Oh, in decomposition. I thought you said in conversation.
No.
I was like, yeah, of course, every day. Sorry. Yeah, in decomposition, probably when we're talking about like radioactive materials. Okay? Radioactive, no?
Yeah.
Yeah, okay. There was also a video game called Half-Life, but that was a few years ago. And I never played it. I just knew it existed. All right. So this is the amount of time needed for a quantity to be halved. How long before I have half of what I started with? Okie doke. So here's our problem. Okay. We're probably only going to do 2-ish examples. But I'm going to have lots of follow-up questions for each example. And these follow-up questions are like varieties of things I might ask you regarding growth problems or decay problems. Probably not all of them at once, but maybe this or maybe that, that kind of thing. Okay, so let's say a bacteria culture grows exponentially. So let us then say the culture that started with 25 bacteria has grown to 350 bacteria in 9.996 days. We were very precise when we were counting. Okay, first question that I'm going to ask you. Possibly. Is, what is the growth rate of this bacteria? Now, if you look at the numbers that I gave you versus the variables we had over here, isn't that the only unknown? Did I give you the initial amount? Cool. Did I give you some amount for some specific amount of time? There was 350 after 9.996 days, right? So the only thing we don't know out of this is the K. So we're going to plug in everything where it belongs. So Y, the population, is 350. This equals the initial amount, 25, times e to the k times t power, so 9.996 k power. Okay. Now here's the good news. Once we find this growth rate is going to be constant for the rest of the problem. Okay? Now, when we do example 2, it's going to be a different k, right? But for this problem, we're going to be able to keep this k. So if I want to solve for k, where is it? What kind of equation is this that I need to solve? This is an exponential equation. And how do we solve exponential equations? We're going to take the log of both sides, but before we do, we got to contend with that 25. Okay? So how do I get rid of this 25? Divide it off. So E to the 9.996K equals, what is 350 divided by 25? 14? Oh, how nice. Okay, now what? I can take the natural log of both sides, and why especially natural log? Because it's base E, and they just cancel. So the exponent 9.996K equals the natural log of 14. Last step to solve for K. That's multiplication, right? What gets rid of multiplication? So K equals the natural log of 14 divided by 9.996, which works out to be that much. Okay. Is that a reasonable number to get? Is that an expected number? Is this a growth problem? My population is getting bigger, right? So should my growth rate be positive or negative? It should be positive, and that's what we got. Okay? So on, what's the next time we see each other? Thursday? I'll have a couple things for you. I'll have a printed copy of the review for everybody. I'll have a printed copy of the take-home test for you. And we'll wrap up this problem. It'll take probably about 15 minutes or so to do the rest of these problems, at least to my content.